All right, are you ready for some info dumping? Hopefully not, because hopefully this won't be info dumping. But there's a lot of terminology that we're going to talk about in this chapter, okay? So some of this should be familiar. I'm not going to give precise definitions. If you want more precise definitions, check out this section in the textbook. It's all under 5.1. A few chapters ago, each section in this guy's book was like 2 paragraphs, and now a section is like 30 pages. So, but it is in section 5.1. We're breaking up that section into about 10 pieces. Okay, so here we have a graph. You've seen graphs before. And basically what a graph is a graph is just a collection of edges and vertices. So, right, of course, you know, here, hey, look, these are vertices. That's the plural of vertex, by the way. And then, of course, we have all these edges as well. And the edges are just what connect the vertices. So when we talked about relations, right, the vertices were all the elements in the domain. And the edges, well, we talked about digraphs, but here we have an undirected graph. Undirected, of course, meaning, right, there's no arrows, they're just connected. And the edges are what relate those two things to each other. So here, this is like a symmetric graph, if you will, a symmetric relation, right? If president is related to Abraham Lincoln is also related to president. Okay, they both have to do with the same concept. So those are edges and vertices, and all graphs is a collection of edges and vertices. Okay, so that's what a graph is. That's what this looks like. And then we can introduce some new terms. So let's say we introduce the term of path. So a path is just a collection of edges that connects to vertexes. Oh, I did it. Vertices. It connects to vertices. So for example, right, we have a path from president to Washington, D.C. These topics are maybe not directly related, although maybe they are directly related. But, right, you can get to Washington, D.C. from president along this path by going through Abraham Lincoln, according to this graph. Okay, so paths just connect, right, vertices through different edges. Oh my gosh. Can we pretend that's a very nice looking E? All right, so again, there is a path that connects president and actor. There is not a path that connects president and Civil War. All right, so again, here is an example of a graph we'll talk later that's not connected. And interestingly enough, we'll also talk about how this graph relates to partitions. We can look at this whole set as a set, and then the two parts that are connected as a partition. So for example, right, this, whoa, oh my gosh. It's like I'm trying to draw and I'm in preschool or something, right? Here's one connected subset. Everything in here, there's a path from one thing here to another thing. We're going to say that means connected. And then here's another part. That would be like the other subset of that partition, right? Here's two things that are connected to each other, but not connected to anything else. All right, I'm really jumping ahead of myself with these definitions, but the point is path, right? So there are path from actor to Ford's Theater, right? There's all these things have paths between them because they're connected, where of course these two things can only have paths to each other. There's no path between these two things and anything else in the graph. All right, and then we've mentioned directed graphs before, right? We talked about digraphs. Well, here's an example of an undirected graph. Right, these are directed. And I've never heard undirected graphs having a cool name either. Like, if this is a digraph, is this an undigraph? I've never heard that. I don't think it's a thing. But yeah, this is an example of an undirected graph. Undirected graphs have to do with symmetric relations. For what I said earlier, right? President is related to Abraham Lincoln. I just tried to circle that with white. President is related to Abraham Lincoln. Abraham Lincoln is related to president. Whew. So That's like a third of the definitions that we need to talk about. But don't worry, we're going to use these definitions to say fun things later. So here we have a digraph. Okay. And I think these are boxers or something. I just took this from the textbook, but I forgot to read up on my boxer language. George Foreman, that's like a grill to me. Is it also a boxer? I've got no clue. But I don't know. Maybe these are people. Maybe these are boxers that have beaten other boxers. I don't know. Or maybe it's Muhammad Ali just likes his George Foreman grill. Who knows? But the point is, this is a digraph. This is a directed graph because, right, it's not symmetric. Muhammad Ali is related to Sonny Liston, but not the other way around. So this is an example of a digraph. Over here, we have something, and I feel like it's really small looking, but over here we have something called a weighted graph. Okay, there are weights or costs. I don't really love the word weights here, but a lot of times when we think about weighted graphs, oh, that has a T in it, there's going to be costs or distances on those edges. And these can be digraphs or they can be undirected graphs. So here we have an undirected weighted graph. And you can think of this as the distance between these two cities. So from, actually, Washington, D.C. is not a city. Is it? Maybe that's an embarrassing thing to ask. Anyway, from Washington, D.C. to Fredericksburg is maybe 50 miles. Fredericksburg to Richmond is 60 miles. And now these topics, right, of paths have very physical meanings as well, right? The path from Washington, D.C. to Richmond is 110 miles, right? And then there's also a path, yeah, you got the idea, okay? And it could also be costs if we're thinking of like purchasing something or like unlocking things. If I'm thinking about like video games, you could also make graphs like that. Okay, so the last concept in this video, in this little rapid fire definition slinging, we'll be referring, and don't worry, we're going to be referring to these definitions. We're going to be referring to these examples all throughout this chapter. So we'll be refreshing. I want to talk about graph isomorphisms. Okay. And that's a very fancy term for just saying the same graph with different names. So graph isomorphism is our last definition for this video. And it basically means same graph, different names. So if I wanted to, right, maybe I make this other graph, and this other graph is maybe let's say we have node A, we have node B, we have node C, and we have node D over here, and maybe it's 50 to get from here, and then 60 to get from here, and 150 to get here, and 100 here. Well, okay. Are these the same graph? Well, no, one has cities and one has letters. But mathematically speaking, these two are the same graphs. These are isomorphic to each other. Because yes, they're talking about different things, but mathematically speaking, they are exactly the same. And it turns out it doesn't even matter where these nodes are, right? I could have written node A over here. And as long as I have the node, like the edges in the same spots, it would be the same graph as well, but we'll talk about that in a future video. Okay. So those are just some things that we're going to talk about when we talk about graphs, vertices and edges. We'll talk about paths. Paths are going to be useful for finding shortest paths or traversing graphs. Remember, undirected or directed graphs, depending on whether there's arrows or not. Weighted graphs that include costs and distances, and graph isomorphisms, which basically just say a rose by any other name smells just as sweet, or something. I don't know. Anyway, enjoy, and see you in the next one.